I misread? Okay, sorry. Just thinking. What's the integral of E dot dA?
Just EA?
Say it again?
Just EA?
What is, okay, what's EA? If the electric field's constant, pardon?
Flux.
Say it again?
Flux.
Uh,
Electric flux.
yes, and so what do you think is B dot dA?
Magnetic flux.
Yes, this is just the magnetic flux. If the magnetic field is constant, we have that. But the more generalized case, the integral of D dot dA. Now, if you look at various videos or notes of mine, sometimes they'll use a subscript B, sometimes they'll use a subscript M. They both stand for magnetic flux. And it is a capital Phi. All right, so this is a huge breakthrough that there is a connection between a magnetic field and a current. And if there's a current flowing, there's an electric field that must be causing, because remember, when we started out, we looked at the different ways of explaining why objects, why particles, charged particles move. One of them was electric field. There also has to be an electric potential difference, or a voltage. So we're producing a voltage by changing the magnetic flux. My understanding of the history is that Lentz, a Russian physicist, was the one who came up with the formal mathematics of it, although usually he's credited with just the negative sign. The EMF is equal to the negative change in the magnetic flux with respect to time. So we have this parallel again of E dot dl is equal to d phi dt. Over here we have B dot dl is equal to d phi dt plus this pesky little thing right here. But this pesky little thing right here happens because we can have an individual charge that's moving, whereas with magnets, until they find a monopole, with magnets, you will always have a north and south traveling together. So let's take a look at some units. The units of the EMF have to be the units of the magnetic flux over the units of time. What are the units of the EMF? Units of magnetic flux. It's written over there as a hint.
Volt seconds.
It would be equal to a volt second. Yes, I guess I will accept that. The direct unit is the Weber. Weber per second. Now, the magnetic flux is B times A, so that would be a Tesla meter squared per second. And well, let's see if this actually works. I know that F equals QVB in terms of units, so a Newton is equal to a Coulomb meter per second Tesla. So a Tesla would be a Newton second per Coulomb meter. For those who have had me before, a Newton second is also what I usually define as a Descartes. If you haven't had me, it's a made-up unit. So this is a Newton second per Coulomb meter times meter squared per second. Seconds cancel, that cancels out with that, and I'm left with a Newton meter per Coulomb. And Newton meter is and a volt is a joule per coulomb. So it all works in that wonderfully convoluted way. But that gives us another unit of time. Second is a Weber per volt. All right, so it is producing, so we have this magnetic flux that is changing. The significance of the minus sign is, well, in essence, nature doesn't want a runaway process. Let's be a little bit more explicit. Anyway, Maxwell's equations. Let's say I've got a loop of wire that is moving this way. I have a region of space over here with a magnetic field coming out of the board. So before it gets to this place with a magnetic field, an external magnetic field, there's no magnetic field going through my square of wire or rectangle of wire, and therefore the magnetic flux is zero and it's staying zero. No change in the flux, no currents induced. No voltage produced, no current induced. When it enters, is the magnetic flux increasing or decreasing? We have B dot A, which was written on the board.
Increasing.
Why?
Increased area.
Yes. My area is, the area where the magnetic flux is increasing, therefore my flux is increasing. Therefore the flux is increasing. If my magnetic flux is increasing, I am going, therefore there's a change, and therefore the EMF that is induced is going to produce a current that wants to stop that increase. So which way will the current be flowing through the wire? Well, if the current flows counterclockwise, the magnetic field it produces, the secondary magnetic field, is going to be in the same direction as this. Nature just says no. If the current flowing around like that, the magnetic field that's produced is going to be into the board, countering this. So this will produce a magnetic field going, it will produce a current that is going clockwise, because it wants to oppose the change. If it went in the counterclockwise direction, producing a magnetic field that bolstered this, well, that means we have a magnetic field increasing, which is going to cause a change in the magnetic flux, which means that it's going to cause it to increase more, and we get this runaway process. Free energy or the destruction of all mankind. Well, and probably all life. So nature does not want a runaway process. Although there are some theoretical bombs that would cause a chain reaction throughout the entire atmosphere, but that's a different story. Now, now the thing is immersed in it, how is the magnetic flux changing now? And assume all my rectangles are the same size, all my rectangle of wire.
Which way is the magnetic field like pointing?
Coming at you.
Okay.
Those are supposed to all be dots, blue dots. What's happening to the magnetic flux? It's not zero.
Increase again to its maximum,
So why is it increasing?
or at least from where it was last time.
Oh yeah, I'm talking about once the whole thing is in this magnetic field.
Should
Yeah. So what would be the induced current?
Zero.
All right. Yep. So now it's leaving. As it leaves, what's happening to the magnetic flux?
Decreasing.
And nature says, no, I don't want it to decrease. And so it's going to produce a current. Well, the change produces an EMF, which creates a current, which wants to counter the change. Well, since I'm getting smaller here, it wants to boost it up, and so it's going to create a magnetic field in the direction of the external magnetic field, and so we'll get a current flowing this way. So in this same piece of wire, we'll have current flowing one way, and then it'll switch going the other direction. Hopefully you can see a potential application here of creating alternating current. All I need is a uniform magnetic field, and I take a piece of wire, and I don't have to move it through like that. If I spin it, it does the same effect. And the way most major power plants in Europe work with DC power, it's the same thing. The difference is the coupling. That when it's after the current's been generated, it goes out somewhere, and there's a connection piece that called the coupling, which determines whether it's AC or DC. So we now have a way of creating current from a magnetic field. So let's take a look at a problem. I have 4 wires here. They're all bare, no insulation. But I have wires things can conduct. We've got a magnetic field that's coming out at us because dots are easier than crosses. This wire is moving this way at 2 meters per second. This wire is moving this way at 3 meters per second. What is the current generated? Assuming that the wires stay within this uniform magnetic field the entire time. So some uniform magnetic field, let's give it a value, I'll make it 4 Tesla. Let's give some units that this initial distance is, let's say 5 meters, and that initial distance is 6 meters. Oh, and we'll just set a resistance of 7 ohms. All right, so I know that the EMF that is going to be produced is I times R, and it's got to be equal to, I'm not worried about the minus sign, we'll think through the direction. d phi b dt. Phi is ddt of v times a. My magnetic field's coming out of the board. We'll make the area out of the board. Also, it's a flat surface, so I could make the area in the other direction, but A will come out this way. And so this just becomes ddt of BA. My magnetic field is constant, so I can just factor that out. So I get ddt, so I have V times ddt of A. Area is length times width. And my length and width are both changing. So I'm now down to my EMF is my magnetic field times product rule, product rule. L dw dt plus WD L dt. So this epsilon is equal to 4 Tesla times my length, and let's make that one my length and that one my width. 6 times the rate at which my width is changing, which is 3 at that moment, plus my width times the rate at which my length is changing at that moment. So that's 6 meters, 3 meters per second, 5 meters, 2 meters per second. And so 18, 28, 116. I got a nod back there.
Yeah.
All right. Units?
Volts.
Yep. 4 Tesla meters squared per second. And I know that's going to be equal to the current that is induced at that moment times my resistance, which is 7 ohms. And so my current is 112 sevenths, which is something absolutely magical, amperes. In which direction will the current flow? Your choices are clockwise or counterclockwise. Or if you just want to be contrary, there is no current, but that's not the answer. Unless it's a Z code. All right, what's happening to the magnetic flux? Increasing or decreasing?
Increasing.
All right, so if the magnetic flux is increasing, the induced current in the wires will want to do what? Does it want to help it or slow it down?
Slow it down.
So in order to slow it down, which way will the magnetic field, that current, the secondary magnetic field, which way will that have to go?
Negative.
Into the
Okay. And so which way does the current need to flow in order to produce that?
clockwise.
So my current will flow around like that, producing a secondary magnetic field into the board.
If we give our answer, how do we put that, like after we have I equals 112/7 amperes, what would we look at?
On this particular problem, since it's on I have it presented on a flat surface, you can say clockwise would be fine here. Because if I'm looking at it, if I gave you an I hat, J hat, and K hat direction, then go that route. So if I went with the traditional I hat, J hat, K hat, then it'd be in the negative K hat direction. No, sorry. It has to be clockwise or counterclockwise. The magnetic field that produces this in the negative K hat direction, but the current itself is clockwise or counterclockwise. questions? Other questions?
So is it the flux or the field that's trying to not run away?
The nature wants the magnetic flux not to run away. And there are only two ways of doing that. One is to change the area, or one is to change the field. And in this case, it's the field. I'll talk about the area part in just a moment. Other questions? I assume I answered your question, right? All right. I now take what I refer to often in problems as a U-shaped piece of wire. I'm not quite sure how else to describe that. And I've got a wire on here that is going to move at some speed v. I have some length this way, and I have a width going this way. We're going to do something very similar to what we just did, just more narrow in the fact that I have only one side moving. I have a magnetic field, of course, constant uniform magnetic field that is bathing this. And I'm going to look at the EMF that is produced. The EMF is going to be, the magnitude is going to be d phi b dt. Very similar. A related topic, although it might not seem obvious right now, who's seen The Princess Bride? One of you. The rest of you really should see it. It's incredible. It is a great movie. And then integral of v dot dA